Welcome back. In the last video, we defined linear transformation, and we are going to prove that more examples are linear transformation here. So in example 2.1.2, we'll be looking at polynomials. I'm going to look at the map that sends p of x to x times p of x. So from polynomials of degree n to polynomials of degree n plus 1 or less. All right, I want to show that t is a linear map. So again, whenever you want to do this, you want to prove these two properties. You want to prove that scalar multiplication and addition are preserved. So let's do that. I'm going to take p1 of x and p2 of x in Pn, and I'm going to take k in R. All right, first condition. I want to look at t of kp1. So that's x times kp1. Well, I could write that as k times xp1 of x. And now this part here, that's our function on p1. So that's k times t p1 of x. That's it. Property 1 is done. Let's try property 2. What if I add these polynomials first and apply t? Well, that means I would multiply x to the sum. But these are polynomials, so I know I can distribute the x in. This part is t of p1, this part is t of p2, and so we do get that t sends a sum to a sum. And so yes, t is a linear transformation. All right, let's try another one. I'm asked to determine whether the following function is a linear transformation. All right, so this is a bit more challenging because I'm not telling you whether it is or not, so that's part of what you have to do. The map sends t of A to A transpose. It looks pretty natural. Let's try to prove it. We can always backtrack when we find an error or if we get stuck. So I'm going to take two matrices in M, N, and I'm going to take k in R as usual. First, I'm going to look at t of ka1. So that's going to take my matrix ka1 and transpose it. Now, we can use properties of transposes that we've learned in linear. The k just comes out. All right, and so that's perfect. That's what we wanted to see. We wanted to see the t separate from the rest. And so, yes, it's k times ta1. First property holds. Let's try the second one. I can bring the transpose into a sum. It's only when you have a product that you had to switch the order, but the product of matrices doesn't actually appear when you're talking about vector spaces. It's only scalar multiplication and addition, and those act well with the transpose. And so, yep, I get the sum, and so property 2 holds as well. And so, yes, it turns out this one is a linear transformation.